We said last time a map or just a function from a plane region into another plane region can be used to make some integrations easier. So we can consider the UV plane instead of the XY plane. Maybe we have a region like this, we said, that's part of a wedge. Well, if you switch the polar coordinates, it becomes a rectangle, right? Like if this goes between, think of U is R and V is theta, so between R1, that radius, and R2, that radius, or U1. And between two angles, V1 and V2, if we put it in a U1, U2 space, this little wedge here actually becomes a rectangle. Then you have constant endpoints to integrate over in R theta space or UV space, instead of these awkward curves to integrate along in XY space. So we introduced the Jacobian to be able to evaluate integrals in that space. And one of the first things I wanted to do was point out that the easiest coordinate transformations are just linear transformations. This phi UV notation is awkward. This is x equals u plus v, v and y equals u minus v is another way of putting that. Is a linear transformation. So let me instead here. So linear changes of coordinates or linear transformations. In these, we consider x given as a AU plus BV, y equals CU plus DV, where A, B, and C and D are just numbers. So these are linear transformations. We call it some map phi, and the idea is it takes and maps regions in the UV plane. Let's do something like this. Some region in the UV plane D0. Each point in here, UV, if you put it in, gives you a corresponding coordinate in XY space. In some region D. And for these, an interesting thing happens. These actually map or take point lines in UV space to lines, and correspondingly lines back to lines in the other space if you have an inverse transformation. And parallelograms to parallelograms, in fact. It keeps parallel lines parallel. Parallel lines. Parallel lines. And because this is a continuous transformation, it'll map the interior in one space to the interior in another. The idea is whenever you have a continuous map, and certainly a linear map is a continuous map, you can't just be mapping points inside this space and moving along and then have it suddenly jump outside the region in this space. So what happens is each one of these points on the UV in UV space is mapped to another point in XY space. And because the transformation is linear, the line here maps to a line here, a line here maps to a line here. And so the boundary of lines will map to a boundary of lines here. And the points inside will map to either all the points inside or all the points outside. But it has to for a continuous map, it can't map partly inside and partly outside. So we'll map the inside of this region into the inside of this region. And we can consider some integrating over region one space, integrating over region the other space. Ideally, what you want to do is take, well, with linear maps, it'll take the parallelograms to parallelograms is what it'll do. So here's an example map here. Suppose I let x equal u minus b and y equal u plus b. Sorry, x equals u plus b. Y equals u minus b. This is a linear transformation, right? A is 1, B is 1, C is 1, and D is minus 1. And then I'll say A, what is the image of the axes? So first the u axis in xy space. Well, the u axis is v equals 0, and it gives us these corresponding curves in xy space. X equals u, y equals u. Well, what's that? That's a parametric line, right? X and y written as a function of one parameter, u. And if you solve for x in terms of y in terms of that, it's x equals y. So we have this space right here, and this is the u axis mapped in b equals 0, if you like, mapped in xy space. And then correspondingly, the v axis, where does that map to? Well, the v axis is u equals 0. Is again, you put v equals 0, you got x equals
yeah, it'll be x equals b.
This is v equals 0. No, wait a minute.
Yeah,
V equals
no, it's u. You're right.
Yeah, u equals 0. Now we get x equals v and y equals minus v. So it's this is parametric equations for the line by eliminating the parameter v. X equals v, y equals minus v. You get y equals minus x is the line, and so it maps these lines to these lines. This is the u equals 0 line, and so what it's really doing, we mentioned this one last time, is just changing your axes, but it still keeps the axes straight lines when you do a linear transformation. All right, so the next page. I suppose we wanted to do an integral here. We could do something like this. Suppose we take this linear transformation and we want to apply it to this parallelogram. Parallelogram in XY space with corners 0, 0, 2, 2, 1 minus 1, 3, 1 in XY space. By this mapping. Well, what we have is the XY coordinates, so we have to solve for U and V from X equals U plus V and Y equals U minus V. We can add these two to eliminate V and get X plus Y equals 2U. And you can alternatively subtract to eliminate V, to eliminate U. And then you get X minus Y equals 2V. And this tells you, and what I'm doing is I'm solving for U and V. You add these things to add a multiple of one equation to another, eliminate one variable. Here you get this result. If you add another multiple of one equation, first equation plus minus the second equation, right? So if you call this 1 and 2, this is equation 1 plus equation 2. I just picked that to eliminate V. And I can take equation 1 minus equation 2, subtracting to eliminate U. And then this one tells me that U equals 1/2 X plus 1/2 Y. And this one tells me that V equals 1/2 X minus 1/2 Y. This is the inverse transformation, sometimes called V inverse, by which you then map back from points in UV space into points in XY space. And because the original transformation was linear, the inverse transformation is linear. So the inverse of a linear transformation is also linear. It'll take lines to lines and parallel lines to parallel lines. What's more, it actually takes the origin to the origin, as you just see from the original equations, right? If you have X equals AU plus BV, and U and V are both 0, then X will be 0, and Y is CU plus BV. So if it always takes the origin to the origin, and it takes parallel lines to parallel lines, lines to lines. And so this is the inverse map is also linear. Now, how do we find the image of this parallelogram that was in XY space? All we have to do is find the corners. The get image of the given parallelogram in B in UV space. Right? So here's XY space. I have these 4 corners, and it's up on the notes there too. 0, 0, 2, 2, 1 minus 1. And 3, 1. There's my original region, E or something, in XY space. And then the map B inverse, taking this region over into UV space gives what? Well, all we have to do, since we know this map's lines to lines, all we have to do is find the 4 corners here. So the 4 corners we get just by plugging into this inverse transformation. We already know the origin is going to go to the origin, but we can do it anyway. 0, 0 goes to, well, let's see, U is, this is your XY coordinate, 0, 0. Goes to U equals 1/2 times 0 plus 1/2 times 0. Sure enough, it's 0. And v equals a half times 0 plus a half times 0 is 0. So it takes you to the point 0, 0. And then I take the point 2, 2. Tells me that u is 1/2 2 plus 1/2 2 is equal to 2. But v is 1/2 times x plus 1/2 minus 1/2 times y. 1/2 2 minus 1/2 2 is 0. So that takes it to the point 2, 0. So I have v 0, 0 is the image of this one. We can draw an arrow if we want, if it'll clutter too much. So phi takes that point to that point. And then, let's see, 2, 2, this one right here, goes to the point 2, 0. That's this one. And then the point 1 minus 1 under this map. U becomes 1/2 1 plus 1/2 minus 1 is 0. V 1/2 times 1 minus 1/2 times 1 minus 1 is 1. And so this goes to the 1 minus 1 is mapped to the point 0, 1. So this one here went right here. And then finally, we know where the last point is. Any parallelogram in this space has to be mapped to a parallelogram here, so it has to be parallel to this one. It must be right here. But we can calculate this just to show it. If we take the point 3, 1, then u will be 1/2 3 plus 1/2 1, 2, and v will be 1/2 3 minus 1/2 times 1. Minus 3 halves minus 1/2 is 1. So it is, sure enough, it is the point up here to 1. And what we get over here is a rectangle, right? So this is better. Trying to integrate over this region, if we were trying to do this in XY space, what would we have to do to do a double integral? All right. Well, we take integral x going from the minimum at 0 to the maximum of 3, easy enough. But then on the top, we'd have to have for the top one, this on top for a while, and then this on top for a while, and then we'd have this on bottom for a while, and this on bottom for a while. So we'd have to break the integral into 4 parts, right? What we want to do for the double integral is go minimum to maximum x, bottom curve to top curve, but since it breaks into pieces, I'm going to have an integral from here to here, and then from here to here, and then from here to here. What a mess, right? So rather than breaking it up into those parts like that, if I have this linear transformation here, I can integrate over a nice rectangle that has all constant endpoints. So let's find the Jacobian of the transformation now. The Jacobian of this linear transformation is actually constant for a linear transformation. What is it? We said that the Jacobian, also written as dxy duv, is the determinant of the partial derivatives, dx du, dx dv, dy du, dy dv. And so we can compute those, right? Remember that x was equal to u plus v and y was u minus v. That was the transformation. And so when we put that in, partial of x with respect to u, is just 1, right? Partial of this with respect to u is 1 plus 0. Partial of x with respect to z, 0, v, 0 plus 1, 1 goes here. Partial of y with respect to u is 1, 1 goes here, right? 1 minus 0. Partial of y with respect to v is 0 minus 1 is minus 1. So there it is, and the Jacobian can in general be a function of u and v, but in this case, it comes out to be a constant. That's because it's a linear transformation. So for linear transformations, we'll get a constant because all these are constants. 1 times minus 1 is minus 1. Well, let's write up. Remember what the determinant is. It's this times this minus this times this. 1 times minus 1 minus 1 times 1 gives us negative 2. All right. And what this does is it tells you a magnification factor if you take its absolute value. By our theorem last time, if I want to take a double integral over this plane region D in XY space, it's actually a tilted rectangle, but in general it might be something else. So over this tilted rectangle, special case of parallelogram, of any function f of x, y, I can rewrite that double integral as the double integral of f of x of u and v, y of u and v, over the corresponding region d0 in uv space, if I multiply by this factor in here, the Jacobian absolute value, du dv. And I put dA here. Let's make it more suggestive. Dx dy. So this is the double integral in xy space, and this is the double integral in uv space. And so what is the Jacobian after all? It's a magnifying factor that tells you how much you need to scale this thing by as you transform over here. You notice, for instance, this one actually technically is a rectangle. It's not clear what its dimensions are, but this one only has area 2, and this one actually has area 4. And so the scaling factor there in Jacobian comes out to be 2 between the two. And so for this particular transformation, we can rewrite it as a double integral over this region. U goes from 0 to 2. And V goes from 0 to 1. That's the region here of whatever integrand we have. X is written as U plus V, so it's f of U plus V. And y is u minus v. The Jacobian is 2 du dv. And now we can integrate over these nice constant endpoints in uv space instead of trying to break it up into 3 regions and have tilted lines aside so that the endpoints in here are not constants. Can make your integration much easier, right? So let's do this. D, evaluate for the double integral of x squared minus y squared over the original region D in xy space. Let's call it dA. There's different notations. Sometimes I'll put dA xy to indicate you're taking the double integral in xy space. Sometimes I'll just put dx dy in there. It's very frustrating. Maybe I better just put it back the way it was. Dy dx dy. Suppose I wanted to evaluate this double integral. Well, then I could say, well, according to this thing here, this is just the double integral over t, and x squared minus y squared is x plus y times x minus y. Well, I'll write it like that so I can switch it over to uv coordinates, because I know after all x plus y is u and x minus y is v. So this is the double integral. And, maybe I better just, I'll put it one step at a time. I'm jumping one step ahead. X squared, let's just do it slowly, is u plus v squared, and y squared is u minus v squared. And we need it out. We're going to switch this over to integral the region d0, du dv. But if you square these out, oops, Jacobian. Okay. If you square these out, you get u squared here minus u squared here, v squared here minus v squared here. What you have is 2uv here plus 2uv here comes out to 4uv. Except I left this off. Let's see. Oh, that's right. Okay.
How'd you get 4?
This one is u squared plus 2uv plus v squared.
Oh,
This one is u squared minus 2uv plus v squared. And when I subtract, this cancels this cancels this, and I've got 2uv minus a minus 2uv gives me 4uv.
okay, yeah, I can see it. Thank you.
All right, and so it's 4uv, and then the Jacobian is 2, and the u dv. And since I'm now integrating over the rectangle here, d0, u goes from 0 to 2 inside, and v just goes from 0 to 1 on the outside, and I can evaluate this integral instead. Now, this is nice here because with constant endpoints, I get an additional break, right? I can pull the 8 outside in any case. And then u goes from 0 to 1. And since this one is a constant, you can pull the v out into the v integral. And then you pull the dv through, because without the v in here, this is just a constant, right? U goes between constant endpoints. So this integral will be a constant, and I wind up with this. Integral from 0 to 1 v dv, integral from 0 to 2 u du. So the 4 times 2 comes out front. I can pass the v and dv out of here being constant within the inside integral and rewrite it like that. So this is just 8 times v squared over 2 evaluated at 0 to 1 times u squared over 2 evaluated at 0 and 2. Well, this one comes out to be 2. Right? And this one comes out to be a half. And they cancel each other, and we just come out with this being equal.
I know I should have asked you sooner, but for your bounds, how did you get your bounds?
Oh, the bounds come from the map. Yeah, please ask me questions. Because the idea was that we had an original region that looked like this, right? And then we mapped it over to a region that went from 0 to 2 and 0 to 1. And so instead of going over the region D in the original problem, which I don't, the bounds are very hard because I have to go and break an integral into 3 parts and have this line on top and this on bottom, this on top and this on bottom and this on top and this on bottom. Each one, it's a line, so you have to write the inside integral as y as a function of x is a mess. Instead, in this region, since u goes from, we found out that the corresponding region G0, u goes from 0 to 2 and v goes from 0 to 1. Since, right, this is the new region, we just go x goes from min to max and then bottom curve to top curve is just constant 0 to 2 for u and 0 to 1 for v. So the constants come from the shape of the new region in UV space.
Okay.
So that was the idea. If you have an odd shaped region like this, if you map it into something easy like a rectangle, then it'll have constant endpoints.
Okay, so it came from the height and width of the new region.
Yeah, you take the endpoints of the new region and just treat it as a type 1 or a type 2 region.
Oh, okay, cool.
So that's a simple linear transformation, but this Jacobian applies more generally. But the idea is actually, if you look at the map, let's make this side comment here, just to give you an idea what's going on. Where does the Jacobian come from? If you were to take an XY unit, where, right? 0 to 1 and 0 to 1. Where would that map in UV space? Right? Well, U is equal to 1/2 x plus 1/2 y. So this, so this corner here maps to 0, 0. And 1/2 times 1 plus 1/2 times 0. This one maps to 0. U becomes 1/2 and V becomes 1/2. So it puts it right here. And the 1, 1 point becomes 1, 0. Let's see, 1, 0. Yeah, it's 1. This point 1 here, 1, 1 here, if you compute x is u plus v, I'm sorry, u is 1/2 x plus 1/2 y is 1, and v is 1/2 x minus 1/2 y is 0. It goes to this point. And then the other one comes out here at 1/2 minus 1/2. What happens is the diamond here having, what's this is 1, 0. Yeah. The diamond here having these lengths. This is 1 over square root 2 for this side, 1 over square root 2 for this side. Is actually exactly half the area of this one. And so you have to put the magnification error in. The Jacobian tells you that the area of the one is exactly twice the area of the other. So the Jacobian equals, absolute value of the Jacobian equals 2, is the scaling factor between these little parallelograms in UV space and the original rectangles in XY space. And because linear transformations take every little square like this to a little parallelogram like that, when you try and integrate over UV space, what they're doing is thinking of adding up all these little region here corresponding to those region here. So Jacobian, absolute value of the Jacobian is a magnification between the corresponding little regions here and the corresponding little region. But it's constant because each rectangle here gets mapped to the same shape parallelogram here. More generally, you can do this with nonlinear coordinates. but then the Jacobian varies. It will take little unit squares here at a big different sizes depending on where you're on the plane. So, but nonlinear transformations, Jacobian is not a constant. Okay. Let's leave that one there then. Now I want to do applications hereof. I'll say similarly in 3 dimensions. This is not restricted to 2 dimensions. Suppose we're given a transformation of coordinates. X is a function of u, v, and w. Y is a function of u, v, and w. And z is a function of u, v, and w. Those are in 3 dimensions and that happens. If the Jacobian is not equal to 0, is continuous, same thing as we had in functions of 2 variables, on a region D. I'll call it a nice region D. You just want to avoid fractals and that kind of thing. Number of edges. If you have anything that's like a region that's a finite number of piecewise smooth curves put together, like you get in engineering, then this will be a nice region and this will work. If you have an infinite number of corners or something like that, then this doesn't necessarily work. If it's continuous on a nice solid instead of plane region in X, Y, Z space, let's call it D0 and the W space, and of one sign, positive or negative. Well, actually, if you just leave it not equal to 0 continuous, that's good enough. So if the Jacobian is at 0 and is continuous, it'll be of one sign. Then the image of the image D of D0 in XYZ space corresponds on corresponding solid D has a nice integral formula also. So in 3 dimensions, what you're thinking is I'm in XYZ space and maybe I've got some strange region that I don't like to integrate over. It doesn't have to be a parallelogram. It can be anything, a whole lot of solids there. But the idea is I have a region, a map phi of that form makes X, Y, and Z such that the Jacobian is continuous and not equal to 0. Then it will map the interior region of some some solid over here. Into the interior of the region of the subsolid over there, we can call this D0. And it's such that the triple integral, actually maybe we should call this G and G0 for solids and W and W0. Here's W of W0, just to make it not the same letters we use for plane. Then the triple integral over the solid W in XYZ space of f of XYZ dV will be equal to the triple integral over W0 of, you have to write X, Y, and Z as functions of U, V, and W to be able to do the. But furthermore, you have a magnification factor, which again is the magnification between the little infinitesimal region solids this time instead of plane regions. You take this, replacing X, Y, and Z in terms of U, V, and W, and then you put the absolute value of the Jacobian, du, dv, dw. And so you can integrate it over, hopefully, a nicer region in UV, W space than you had in X, Y, and Z space. So that's the corresponding three-dimensional theorem. It's a Jacobian again, but now the Jacobian is a 3x3 determinant. And so this extends to higher dimensions too, as you might guess, right? It's just dx du, dx dv, dx dw, dy du, dy dv, dy dw. And then dz du, dz dv, dz dw. And again, the absolute value of the Jacobian is the magnification factor. And again, this is a determinant, not a matrix. So it's a determinant of the matrix. So it's just a single function that you have to remember how to do the determinant for. Let's do an example of that one. Suppose I want to make a transformation of this form. Suppose I want to make x equal rho, and instead of UVW, I'll use rho, theta, and phi. Is rho cosine theta sine phi. Y is rho sine theta sine phi. And Z is rho cosine theta. Right? Rho cosine phi. We know these as spherical coordinates, right? Rho, theta, and phi. And this is a coordinate transformation, nonlinear, between spherical and rectangular coordinates. Right? Find the formula for coordinate transformations of integrals. In spherical coordinates. Right? So first I need to calculate the Jacobian, right? The Jacobian is now a 3x3 determinant. And it looks like this. It's dx d rho, dx d theta, dx d phi, dy d rho, dy d theta, and dy d phi. And then dz d rho, dz d theta, and dz d phi. So I need to calculate all those. And we get something that's not a constant function because this isn't a linear transformation. Dx d rho, treating theta and phi as variables, is just cosine theta sine phi. Dx d theta is rho times minus sine theta sine phi. So minus rho sine theta sine phi. And then dx d phi is rho cosine theta cosine phi. Then the second row, dy d rho is sine theta sine phi. Dy d theta rho cosine theta sine phi. And then dy d phi rho cosine theta or rho sine theta cosine phi. And then finally, partial of z with respect to rho is 0. Is cosine phi. Cosine partial of z with respect to theta is 0. And partial of z with respect to phi is then minus rho sine phi. So there's the determinant I have to calculate for the Jacobian. And if you expand on the first row in the usual fashion, remember how to do these determinants? You take this one times the determinant of the submatrix gotten by wiping out the row and column that's in. So it's cosine theta sine phi times this determinant, rho cosine theta sine phi, 0, rho sine theta cosine phi minus rho sine phi. So there's this one times this subdeterminant, and then you take minus this element times the subdeterminant got by wiping out its row and column. Remember that for determinants of 3 by 3 from doing the cross product last semester? Does that sound familiar? So minus this one, which is minus rho sine theta sine phi, times the determinant got by wiping out its row and column is these 4 elements. So it's sine theta sine phi, rho sine theta cosine phi, cosine phi minus rho sine phi. And then we add it to, right, this one times its subdeterminant. So you take plus this one times its subdeterminant minus this one times its subdeterminant plus this one times its subdeterminant. Hopefully it all sounds familiar. So plus this one, rho cosine theta cosine phi, and I'll multiply by the determinant I get by wiping out its row and column is these 4 elements. Sine theta sine phi, rho cosine theta sine phi, cosine phi and 0. So,
That's a lot to write down.
yeah, so that's a bunch to write down. But it does actually simplify nicely. Because you can make a poor coordinate transformation, you have a very complicated function for the Jacobian. But it all comes out to be one function, right? This is indeterminate. When you multiply this out, let's see, we got this times this minus this times this. So it's this times this minus 0. So the first part is going to come out to be cosine theta sine phi times rho cosine theta sine phi times minus rho sine phi minus 0 for the other diagonal. The second line, I'm going to minus to minus cancels, and so I'm going to get plus rho sine theta sine phi times the determinant here. This times this minus this times this, so it's sine theta sine phi minus rho sine phi minus the other way, minus this one times this one is minus cosine phi rho sine theta cosine phi. And then finally minus plus this one, plus rho cosine theta cosine phi times this times this is 0, and so I just get minus this times this. It's 0 minus cosine phi times rho cosine theta sine phi. So there it is, the Jacobian for transformation to spherical coordinates, right? How does that multiply out? Let's see. Rho minus rho squared times cosine squared phi, times cosine squared theta times sine squared phi. That's this one. And then plus rho, let's see, there's a minus here. Let's see, now this is rho sine squared phi sine phi, and this is rho cosine squared phi sine theta. So it's rho, it's called rho sine theta sine phi here times this stuff in parentheses is all multiplies out to sine theta. This is sine theta times, oh, there's a minus rho sine theta. So all this stuff in here is minus rho sine theta times sine squared phi plus cosine squared phi, which is 1. So all this stuff in here is just minus rho sine phi. And then finally plus this one. Actually, let's say this is all times, yeah, that's all times rho right here, okay. And then plus down here, we've got rho squared. Actually, it's minus, I guess, by the time we're done, right? Minus rho squared. Cosine squared theta times cosine squared phi sine phi. So it looks like that. All right, and now what we've got is minus rho squared on each of these terms. And the first one gives cosine squared theta sine squared phi minus, no, there's minus out here. This one gives sine squared theta sine phi and this one gives cosine squared theta cosine squared phi sine phi. And with a little finagling here, look, we've got cosine squared sine squared plus sine squared sine is cosine squared
The theta and the,
It's like I'm missing a sine phi here. It looks like I've got sine phi cubed there. Want to make sure I got this right. Yeah, sine phi cubed. This one. Okay, and now that's sine cubed here. Now this one plus this one is sine squared plus cosine squared. Let's see, one of these. Okay, this one plus this one is cosine squared theta plus sine squared. Yeah, is sine squared phi plus cosine squared phi times cosine squared sine phi. So these all come together to make cosine squared theta sine squared phi. Because the cosine squared plus sine squared just become one. And then this one, they come in here, and then this one becomes sine squared theta sine phi. Will work there. So this becomes minus rho squared. Now sine squared plus cosine squared here is one. And this is sine, I'm sorry, sine to the first power. Yeah. These two, right? The sine squared plus cosine squared leaves one sine here. And so these two combine together to make this thing. Times minus rho squared. And this one comes down here, and now you've got cosine squared plus sine squared times sine phi. This comes out to be minus rho squared sine phi. And consequently, what that shows is the Jacobian formula that we have is the triple integral in the rectangular coordinates of a function of x, y, and z, dx, dy, dz, can be written as the triple integral in spherical coordinates over a region W0 of f of x of rho theta phi, y of rho theta phi, z of rho theta phi. Times the absolute value of the Jacobian times d rho, d theta, or d phi, d theta, let's say. Well, what's the Jacobian? It's rho squared sine phi. So this is the triple integral of f of all this stuff again. Rho squared sine phi becomes the Jacobian. D rho, d phi, d theta, precisely the formula we had before. This factor that we had in here from taking the non-rectangular region is actually the absolute value of the Jacobian. That just shows how you can compute it for spherical coordinates, and then you can compute it similar for other. That's the example of computing the Jacobian and then figuring what's the integral transformation thing, and it verifies our derivation before for spherical coordinates. This one's a little tricky. Did you see how I did that? Cosine squared, sine squared, and cosine squared. Cosine squared adds up to just cosine squared. Sine squared plus cosine squared is 1. Each one of these multiplies sine phi. So that comes out there. Okay. Now there's some applications of this. And we've mentioned these before. For an object of mass density delta, and what does it look like here, of x, y, z, at each point x, y, z in a solid W, we have the following result. The total mass of a solid M is going to be the triple integral of the density function x, y, z dv integrated over the solid. So if you've got a solid that's not nice in rectangular coordinates, you can switch it to some other coordinates where it is nicer. Cylindrical, spherical, or your own designer coordinates. Then what about the center of mass, or the book will call it center of gravity, which is the same if you have a uniform gravitational field. But I dislike the term, and I think they should call it center of mass. What is that going to be? Well, what you do is you take the mean mass point that you get by integrating over, well, let's write it this way. It's the moment of mass called it MYZ over M, where MYZ is the moment about the YZ plane, is the triple integral over the solid of X times the density. So they call this the moment of mass about the YZ plane. And then similarly, you can compute, this is X bar, is the X coordinate. And then Y bar is the Y coordinate is MXZ over M, where M is the mass you just computed. And MXZ is the moment about the XZ plane, is the triple integral over the solid of Y times the density. And then finally, Z bar, the Z coordinate of the center of mass, is MXY over M, where MXY is the moment about the XY plane, is the triple integral of Z over the solid. All right, so there's formulas for calculating mass and center of mass using these moments of mass. I have an example here. Let's see. And then in 2 dimensions, there's a corresponding formula also. I've just done the triple, the 3-dimensional case here. So here's an example of it. Maybe I'll put it on the screen just to save a little time here. So with those formulas, suppose I want to, oh, sorry, this is the charge one. You can do that with mass. You can also do it with charge inside a solid. If you integrate the charge density, then you get the total enclosed charge in the solid. So you can get total mass of the solid or total enclosed charge. Here we'll say, if you just replace this with, find the mass of the solid, if the if the mass density is 2 times 10 to the minus 10 over square root x squared plus y squared plus z squared. So you can do this with charging, do it with mass, but the idea is that the total charge of the total mass is the triple integral of the density function. Here's the density function over the solid, right? That's the definition. Well, if this is a solid in spherical coordinates, or inside a sphere, x squared plus y squared plus z squared less than or equal to 0.6, 0.16, that's 0.4 squared. This is a sphere of radius 0.4, right? This being the square of 0.4. And so what I want to do to integrate over the whole solid, this charge density or mass density, is to integrate in spherical coordinates, which means I have to put the factor rho squared sine phi that we just revalidated there, d rho d phi d theta. And this is the integral over the sphere. Let theta go from 0 to 2 pi, phi go from 0 to pi, and rho go from 0 to the radius of the sphere, sweeps out the sphere in spherical coordinates, right? And here's the nice thing about using spherical coordinates for a sphere. The endpoints are all constants. What we said is the nice things for spherical coordinates are cones because they go between constants, and spheres, they go between constants, and half planes for theta goes between. So this is all the way around, theta going between a constant, phi going all the way down between constants, so rho going between the constant endpoints of the sphere. So I can pull the constant 2 times 10 to the minus 10 out of the integral, and then luckily for us, once again, the integrand is a product of functions of rho and function of phi. So I can split this, since it's in, I can split this up into the product of 3 integrals, right? If I can take the sine phi out of the inside integral because phi is a constant inside the inside integral, it comes out here. Once I do that, what's left is an integral between constant endpoints. So this integral over rho is a constant. I can pull it out of here, and it's just integral rho squared over rho is rho. The charge density was 2 times 10 to the minus 10 over rho. Rho is square root x squared plus y squared plus z squared. So I change that to rho, and then I have the factor again. Anyway, I have rho squared over rho leaves me a rho inside the rho integral. There is no, the d theta can come right through because there's no theta dependence in here. So I just get integral to 0 to 2 pi d theta. And the sine phi needs to stay within the phi integral, and 0 to pi of sine phi d phi. So write this as a product of 3 integrals, since we're lucky enough to have endpoints that don't depend on the variables, and an integrand that splits up into a product of function of phi times a function of rho. Now I just have to do these 3 integrals from calculus 1, right? Integral of sine phi is minus cosine phi, integral of rho is rho squared over 2. I plug in the endpoints and take the difference. I get 6.4 pi times 10 to the minus 9 coulombs for this one. If you're doing a charge, the charge inside the sphere, or if this is a mass density, this would be the mass of the sphere. So there's an application of spherical coordinates. You want to find the charge enclosed inside a sphere. You want to do it in spherical coordinates because you get constant endpoints, plus the density function in this case has a spherical symmetry, right? It's a number divided by rho, the distance you are from the center of the sphere. In practice, what happens if you actually have a metal sphere, all the charge will try and run to the outside to minimize the total potential energy. So this would be like a somewhat insulated sphere, so that you actually have a varying charge inside. Nonetheless, there's a computation if you could have that charge density. All right, and so there's the here's the corresponding formula for a plate. Suppose you have what's called a lamina, a flat plate that's so thin that you can model it as a 2-dimensional object. now the mass is the double integral over dA over the plane region that's the lamina of the charge density, or of the mass density, a function of two variables. So it's exactly the same formula for mass, it's just you're doing a double integral since it's over a plane region instead of over a solid. And then mx is the moment about the x-axis is the double integral of y times the density. It's the same formula, right? It's just a double integral instead of a triple integral. And my, the moment about the y-axis, it's odd, you put y here and x here, but it's the moment about the y-axis, or x equals 0 on the x-axis. Moment about x equals 0 on the y-axis is the double integral of x times the density. And then you say that the x center of mass and y center of mass is my over m is x center of mass, right? It's double integral of x over this, and double integral of and mx over m, the double integral of y over m gives you the y center of mass. And then what good is this? I just made a little point down here. Suppose you have an object that you throw without atmosphere, like a bowling pin or something, and it spins around as it goes along its trajectory. What happens is its center of mass follows a nice parabola in the gravity. Remember you do that in Calculus 1? The object follows a parabola. It's actually its center of mass that's doing that. So that's the point you want to keep track of. It's nice to be able to compute the center of mass, right? All right, well, maybe we should one more page here just real quick. Here's the calculation for the center of mass of this lamina. All right, so it's a plate, and suppose it's bounded on top by the parabola y equals 1 minus x squared, but on the bottom by y equals 0, right? I can compute the mass as the double integral of the density function. Suppose it's constant density 2, so it's a uniform plate, right? Then I double integrate the mass density is just double integral of 2. And if I do this in rectangular coordinates this time, then I go from the minimum value of x to the maximum, minus 1 to 1, the bottom curve to the top curve, y equals 0 to y equals 1 minus x squared. And that gives me the mass, right? Just a double integral to density 2. And if you work out these two integrals, running out of time, so I'll just do it quickly and say you get 8/3. So that's the mass. You just take the double integral of the density function. What's the moment about x equals 0? Here's what you can do on some of the homework problems. This is a uniform density here, right? And so I look at this and I say, that's obvious. I can balance it on my finger right here, right? If it's uniform density. And so without any computation whatsoever, I say my, the moment the y direction is 0, and consequently x center of mass is automatically 0. It's my over m. So you just look at it and say whenever it's symmetric and uniform density, you just put the moment at 0 at the middle point, 0 in this case, and the corresponding center of mass coordinate is 0. Now in the other direction, the y direction, it's not clear if gravity is pointing this direction where it would balance. So I have to compute mx is the double integral of y times the density, right? So it's mx for computing the y balancing coordinate is the double integral of y times density. Well, the density is 2, and so I'm integrating 2y over this. Well, and you just compute the double integral as we did in the last couple of sections. You come out with 16/15. And now if you take this one, the double integral of y, mx over m, for the y center of mass, you get this one, 16/15 over 8/3 comes out to be 2/5. So there's the balance, the center of mass, 0 2/5, and in a uniform gravitational field, if you took this and turned it on its side, you can balance it right at that point. X equals 0, y equals 2/5 right there. That's where it would balance. So these are really nice for important computations, like what's the balancing point of this plate if I turn it on its side. And furthermore, this has an interesting application. This 2 that I put in here when it's a constant, right? When I compute my over m, 2 comes out of the my integral and 2 comes out of the m integral and it cancels. I didn't actually need to put the center of mass in there if it's a constant because they would have canceled. So in other words, If the density is constant, we can cancel it in my over m. And just write that as double integral x dA over the area of the plate, right? This, the mass, when delta, once you cancel the deltas out of here, this is just double integral dA, which is the area of the plate. And then on the top, you just get double integral of x over the plate. And similarly here, y bar, when the densities cancel, because they're constant, you take them out and cancel them. Then you have double integral y dA, and over bottom integral is just the area. And so these things we call the centroid. When you have constant density, the density cancel out, and this position is called this XY position is called the centroid of the lamina or the solid. So centroid is a useful computation because it tells you the center of mass when you have something of constant density like that. Now I'm over, so I'm going to let you go. Sorry about that. Let me give you these problems to look at. And what we want to do is put the test 1 week from today. This will be the last material. I will put practice problems out on D2L tomorrow sometime, possibly tonight. D2L, and this will cover chapter, chapter 14. The last section here is 14.8. What I'd like to do out of there is 1, 3, 15, 19, 21. I have some more, but I think maybe that's too many. Let's just do those. Those can be your computations for these center of mass problems. And we'll just make this on chapter 14, but we omitted 14.4. So the test from 1 week from now will be test Wednesday 14.1 to 14.3 and 14.5 to 14.8. The last section being the center of mass. I'll bring questions on those next time, and I'll put up the practice problems we'll talk about too. Sorry to rush that just a little bit tonight. Trying to catch up from the snow days.
And then our finals is just pretty much all the things that we covered in class, pretty much.
Yeah, the final will be comprehensive, but it will emphasize the material after this first exam.